Turn the video
No, you can keep your video on if you want. It's okay. I'll turn my video on when I'm to begin. I guess still waiting for some more people to join in. We'll start I guess 10 minutes after 7 p.m., which is the Bangladeshi time for,
Okay, thank
for
you.
those of you who are not from Bangladesh here. So yeah, we'll start 10 minutes after the scheduled time to start so that we can allow for more people to enter. But is my audio clear?
Yep, yep, very
Okay,
clear.
perfect,
Thank you.
perfect, perfect. And let me test some stuff then. And my screen is it's it's okay. Like it's
Yep,
viewable without lag. Okay,
yep,
perfect, 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 perfect. That's all I needed to
thanks.
know. Thank you.
Yeah, why do we need that? You want to do this? I'm already here.
No, Robin, nobody was speaking then because we decided to start the class 10 minutes late so that we can accommodate more people to join the session. So we'll begin now, effectively. Terribly sorry for the confusion. Okay. So uh, let's. So I'm audible. Everybody can hear me?
Yes, yes, thank
Perfect.
you.
Perfect, perfect. So I will start recording this session as well. There was one question that was a direct message towards me if whether or not this session is going to be recorded. Yes, indeed, this session is going to be recorded, and I shall press record when we begin officially the session of today, and then I will we will have it uploaded on our YouTube channel. If you're unaware of our YouTube channel, do not worry. As soon as the video is done uploading on our YouTube channel, I will send a message on Slack, notifying everybody that the video is uploaded and the video is processed perfectly, and that you can start viewing it in your at your pleasure, basically. So there's that, and there's another question by Zara Ahmed. I got a question: is the house still open for registration? Uh, I did not understand what that question means. Could you clarify? You can unmute yourself or write a message if whatever pleases you. You mean, is the course still open for registration? Ah, I understand. No, the course is not open for registration anymore. Registrations have officially been closed. Uh, yeah, I think so, unless dire circumstances, which we deal on a case-to-case basis. So I don't. Maybe you can try emailing us, like whoever is it was interested and missed the deadline could email us. Maybe under the most ideal circumstances, we could make. I don't know. Maybe we could consider, but I'm not exactly sure. It'll depend on the decision making of other people as well. So yeah. So yeah. I wouldn't ruin the chance to send us an email so that we can try and figure it out. And so always, everybody, please try to stay active on Slack. Slack is like our preferred method of trying to keep in contact with all of you guys. So just try to stay active on Slack because sometimes on our end, mistakes may occur, like especially with the timings, like the timing conversions and everything, mistakes occur. So oftentimes to rectify or clarify on many things, we'll utilize Slack. And please use the I've opened another channel called Social, and if I'm not mistaken, I've invited all of you. You guys can be as frank and as informal as you want in there. Of course, no cussing and no bad language. It's still an educational platform. But yes, acquaint yourselves. It's a fantastic way of getting to know each other, talking to each other. It's so yeah, use it to your benefit. And also when assignments are going to be coming, uh, we oftentimes a lot of these things things are going to get fleshed out in the coming days as to how we expect you to do things. And for people who have already been a part of this journey with us, already know. But for the people who haven't, this is their first time. It's like we're going to give you assignments, and at the end of the day, like, of course, you're allowed to we encourage you guys to talk to each other and discuss with each other the potential solutions and everything. So yeah, the social channel, use it to your benefit to socialize amongst yourself. And the QFT channel, the general QFT channel, just use it to ask or bombard us with questions, whatever questions you can. We have a couple of we have teachers, teaching assistants, TAs, and us as well as moderators who will try to get back to you as soon as possible. So no question is a stupid question. There's no such thing. So just ask away, and we'll try to get back to you as soon as possible. And if we know the answers, of course. Anywho, so let me start sharing. Okay, so it started recording. Yes, yes, right. So the session is now officially being recorded. Basically, my instructions for the preschool lectures were to give all of you a kind of uh, precursor to what is gonna come with quantum field theory, and with this time we've also incorporated what differentiates this quantum field theory school from last year's quantum field theory school uh, is that we've incorporated like really heavy standard model stuff as well. So if like you really need to get your group theory in order. So uh, so you really need to have your group theory in order to understand the generic terminologies and to work around those things. And it's very important that even if you're not an expert in group theory, at least when somebody mentions, say for example, SU2 group or SU3 group or generators of a group, at the very least, those basics are covered, and you're not uh, you're not shell shocked by these terminologies. And I'm certain a lot of you have already done group theory. So for a lot of you, this will be probably a very introductory, basic kind of like class. But for those of you who maybe not come across group theory, this is just the at most basic requirements, because group theory in and of itself is a huge subject, right? It can spawn courses among courses to courses to courses. So you really have to, and of course, it's a group theory is a mathematical concept, so it can span topics in mathematics, and also applications of group theory span anywhere where group theory and objects of like notions of symmetry can be utilized. So group theory is a vast concept. So we are what we try to do in particle physics and in general like physics, we really try to localize the group theory tools to really understand the dynamics of physical theories, which here is quantum field theory. And yeah, quantum field theory and general relativity, or sorry, not general relativity, special relativity, which is of utmost importance to quantum field theory. So yeah, so it's not gonna be the be all end all of group theory lectures. It's just gonna give you the tools necessary to move forward and to accept the verbiages and the words being used in the quantum field theory and standard model lecture. Of course, uh, the group theory is kind of always when in concordance with quantum field theory. The knowledge of the group theory, when it comes to the average physicist, is always on a what I found is always on a case by case basis. You learn group theory as you progress, unless you're a mathematician, unless you're like you've done group theory separately and really ardently fixated on aspects of group theory in depth, so that you have the breadth of knowledge to then incorporate it into other topics of physics. But group theory, more often than not, for the general average like physics public, is more on a case by case basis. So I'm gonna give you the basics, and then your further instructors will know how to, on a case by case basis, feed you knowledges of group theory. Okay, so that's what I wanted to give. That's my short little monologue on what to expect from this preschool. Okay. So, hi Ahmed, is attending classes live mandatory? If attending live isn't possible, then what will it be a problem? Okay. So, this is a very important question, and it's a very common question. So attending, if I'm not mistaken, attending preschool lectures is not mandatory because preschool lectures are kind of like bridging topics, right? So they're really if even if you know like personally, even if you know group theory, it's good to also get like a nice review of sorts. And if you don't know group theory, I would say class is kind of a mandatory sort of uh, course to go through, basically. But the preschools are not necessarily mandatory for attendance, but the main chunk of the school, the main portion of the school, all the other lectures, they are kind of mandatory, and we expect a certain, I think, if I'm not mistaken, 70 to 80% attendance is mandatory, and we have Zoom logs that categorize and help us on the back end to understand who's attended. So attendance is important to get your certificate at the end of the day, as well as submitting assignments and the final examination. So, of course, there is that freedom that all of these lectures, we try our level best to upload all of these lectures on YouTube, but they're more for a review of sorts. And of course, things can happen in life where uh, unmistakably, like you need to attend something and uh, some emergencies occur. Of course, things can occur, but I would say try to maintain routine attendance because that's marked. And the YouTube lectures are not a scapegoat. They're meant to be a part of a holistic addition to the tools that you have available. We all of us will upload our lecture notes uh, that we collect on our tab or our tablet, uh, iPad or whatever. All of us will upload like worked out materials on Slack and also YouTube. It's just giving you more opportunities to get information and to learn as best as possible, but attendance is still key, right? Okay, I hope I answered that question. Anywho, so we begin with some symmetry basics, and first we begin with the definition of symmetry. Okay? Yes. So symmetry, right? First, before we go with the onslaught of defining what symmetry is, we define what group is. Symmetry, of course, just takes from the normal English definition just utilized here. But the the meat and potatoes of symmetry in group theory, sorry, in physics or dynamical situations, is for example, is group theory, right? So we define group G, right? So a group G is like a set that contains elements. Okay, define it as a set. That is a set containing like elements of group G, which have the elements G, like let's say GI, which is the what is known as the identity element. Then we have G2, G3, so on and so forth. Basically, all all of these GIs belong in our big set G. Okay, where yeah, all of these GIs, which where the I's run from I to let's say, sorry, this is one. These I's run from one to two to three, however many. What is the dimension of your set effectively? Okay. Okay. So a group G is a set containing G with star being an aforementioned operation that you define. Okay, this is very important. Being the defining operation that allows us to define the group. Okay. Specifying this operation is very important. What is an operation? An operation could be something like as basic as the multiplication. This is an operator. This signifies this signifies that that two needs to be multiplied with two. This is an operation of sorts. Addition is an operation. Things like maybe rotation by uh, 180 degree. It's an operation. Anything that causes change to an uh, something that already exists is an operation, right? And of course, it doesn't necessarily have to change. An operation could be like, let's say, two multiplied by one. If multiplication is the operation that uh, is defined, two multiplied by one is unchanged. So there could be operations that are unchanged. There could be operations with elements like two and one. They both exist in your big group G, right? And one here is your identity element, right? Identity elements are defined as elements of the group, which, when operation occurs with other elements of the group, the elements remain unchanged, right? So, like GI, the G2 multiplied by here G1 was identified as the group element, the identity element. G1 will just give you G2. G3 multiplied by G1 will just give you G3. It's not multiplied, it's operation. It's any operation that you can define. This operation could be anything. So the identity element really leaves things unchanged, right? And it's important that your group contains also this identity element. Okay. So the definition of a group really requires four very important uh, cornerstones or theories that it has to abide by. The elements of the group or the group itself have to abide by so that they all form a group. Okay. So one being the composition law, which is the binary operation, like a composition rule, which is just binary operation, which is like G star, an aforementioned operation, G prime belongs to G. As in, you operate on whatever elements you have in your big set G, they will multiply to give an element that also exists in G. So everything is closed form, really. So you can see building up to it how symmetry is coming out of group theory and how we can really utilize group theory to form symmetries. So, like, regardless of whatever element you take in the group and then operate on each other, you will get another element that has to exist in the set that makes the group a group. That makes this that is a set G. Okay, very important, right? So this usually, like, we just denote it as GG prime. Inherently, when we write these things together, there's like an implied star operation that is happening in between, right? Number two, there has to be a unique identity. The key word here is unique. I that belongs to G such that IG is equals to GI, which is equals to G. As I'm sure you guys remember me saying it beforehand, identity element multiplied with any other element, or even the identity element, of course, like I times I will give you I. Identity element with any other element in the group will just give exactly that element, okay? And for all G in G. So I could have just very easily denoted this form, IG is equals to G, and call it over. But no, in group operations, we're all sensitive on what side you operated with, okay? Because let's say, assuming G and G prime belong to your set G, capital G, okay? It might not hold totally true that G times G prime is equals to G prime times G. Can somebody give me an example of a situation where something like this occurs? Like define it as any kind of operation, or and G being an element of any particular thing that comes to mind, maybe?
Matrix operation.
Perfect. It's matrix operations. Uh, matrix operations seldom have the like. I'm not saying not all matrices have this quality, but more often than not, matrices have this quality, and so we call that non-abelian. When G dot G prime minus G prime dot G is not equals to zero, we call these non-abelian. Okay? And if, for example, G dot G prime minus G prime dot G is indeed equals to zero, we call them abelian. Yes, perfect. Angular momentum, a fantastic example. Angular momentum is indeed a fantastic example. Yes, 3D rotations are not commutative as well. Another fantastic example. Okay, so we need a unique identity element, right? Like for example, for multiplication, the unique identity element is 1. There's no other identity element for multiplication other than 1. Okay. So moving forward to our third one is associativity. Associativity is a weaker kind of check mark of sorts for the requirements of group theory. So they can be trivially proven of sorts. Associativity just means like G in such order, G prime dot G double prime is equals to G of G prime G double prime. Okay, which is just G prime G double. Okay. All right. Of course, for all G comma G prime comma G double prime that belong to Z. Finally, we have a unique inverse. Every single element must have its unique inverse, and that unique inverse, of course, needs to exist in the group. Let's say you have uh, G, right? G has a unique inverse, G inverse, which cannot be any other like GI uh, inverses. Okay, they have to be unique, or like let's say G primes. Okay, they have to be unique to the G's. So let's say, for example, the number 2, right? If you're trying to define a set where multiplication is the operation at hand here, the number 2 has the inverse of 1 over 2, right? And 1 over 2 is quite uniquely only 2's inverse. 3 has 1 over 3, for example. And how do you define something to be an inverse? Because like G dot G inverse, so should simply give you your identity element, right? Which I denote as I. G dot G inverse should just give you I. Now, of course, this is also equals to G prime dot G prime inverse, but this G prime inverse and this G inverse never are the same. And very importantly, these inverses have to also be included in your set to make it a group. The group has to be closed. So, okay, to formalize, to write it more neatly, what is a group? It has to have a unique inverse, where for all G that belongs to G, there exists a G inverse, there must exist a G inverse such that G inverse is equals to G inverse G, which is equals to I. And again, as we can see here, multiplying an element with its inverse, you don't really fall in the trouble of what order you multiply them. Left multiplication or right multiplication is the same thing. It'll give you an inverse, okay? Only these two cases are where the order doesn't matter. Every other case, the order will matter. Okay. So as I mentioned before, if the binary operation, this operation, if the binary operation is commutative, as in commutation is this, let's say GG prime, which defines things as G G prime minus G prime G. Commutative implies this equals to zero, and anti-commutative implies this not equal to zero. So if the commutation relationship is indeed equals to zero, then we call them abelian. If they're not equals to zero, then we call them non-abelian. And specific non-abelian cases of group theory are quite fascinating, and we'll come to them as we go into standard model and SUN theories and so on and so forth, gauge theories. Okay, so in physical theories, these quote unquote symmetries kind of amount to the realization where a certain transformation leaves things unchanged. Okay. Now we're getting to it. Now we're getting how symmetries are used. It's like you're using an element and you're causing some kind of transformation, some kind of push, but the something overall, prescription of something overall remains unchanged. Very a very I think if for those of you who have done special theory relativity, for example, like uh, translation, right? The sheer act of uh, translation, it it preserves energy, right? Energy conservation. Energy conservation is preserved. That's the symmetry that's preserved. So that's translation is a kind of transformation that is occurring at your coordinate x mu, and in such a transformation, you can see that the energy is something that remains unchanged. It's conserved, right? So group theory then is the mathematical framework. Then is the mathematical framework of symmetry. All these theorems allow for a lot of exploitation when it comes to us trying to figure out symmetries of theories. Okay. Anywho, so mathematical and every group, very important, is the symmetry is a symmetry of something, or at least itself. At least itself. So let me give you some symmetry examples that we encounter in physics, right? Uh, let's say like variational problems. Variational problems encounter like a high degree of symmetry. For example, let's say for when you're trying to extremize a circle, right? You're doing a variational problem on trying to learn the path of a circle. What is it extremizing? It's basically trying to maximize the area for which it can make that kind of a geometric shape. So there inherently has some symmetry involved with it. So variational problems. Another very, for those of you who are privy to GR, know what is the Minkowski solution or Minkowski space. Another example is the Minkowski space, right? The Minkowski space is a highly symmetric and stable solution to the vacuum Einstein's equations. Minkowski spacetimes exhibit a much higher form of vacuum than any other kind of generic solution that you can find with the Einstein's equation for solutions where your T mu nu is has zero entries, basically. As in like there's no mm, energy momentum tensor. So yeah, and the symmetry of Minkowski space is what is known as so the symmetry of Minkowski is the Poincare symmetry. So Poincare symmetry, like let's say you have some coordinate x prime mu, and upon which some kind of transformation is occurring, right? Let's just keep this blank for the time being. Some type of transformation, some transformation, which we will define as the Lorentz transformation, some transformation of x nu, okay, plus some a mu term. Now this quote unquote some transformation incorporates incorporates the ideas of boost and rotation. Okay, it incorporates the idea of boost and rotation. Now that in and of itself doesn't incorporate like Minkowski spacetimes or like scenarios or like relativistic scenarios because you have to also incorporate translations. So translations come from here, from this term. And what we're saying is Poincare symmetry will effectively lead this x squared term, as in x mu dot x mu, like x squared, which is basically x mu, like right? It's covariant vector, contravariant vector, all dotted together. It's effectively a dot product. This has to be equals to x prime squared. So Poincare symmetry, and you can build it up in such a manner where you have, even if you do some kind of transformation to your x mu, let's say you have your bare x mu and you do some kind of this some transformation, which I'll name it as Lorentz transformation. There's no point in not naming it. Officially, it's called Lorentz transformation and some translation. Uh, uh, Guys in a very elegant form, you will find that this is conserved. X squared, the dot product or the inner product is conserved of these two coordinates. Okay, so that is your building block, right? Because the scalar has to be conserved, and that's how you build up how your Lorentz transformation should look like, right? We have not specified what the Lorentz matrix is going to be, how it should transform with the metric. We're just building merely by symmetry arguments, okay? Merely by symmetry arguments. So yeah, we'll get to it in a little time for Poincare symmetry and like Lorentz symmetry. Let's just go through some of the other examples. So physical theories, where you utilize physical theories, often utilizing various parameters, you will find you sorry, 1 minute. There's a question. Okay, let me answer your question in 1 minute. Let me just write this one. Various parameters. Uh, Various parameters. You will more often than not all of these parameters lead to physical theories. Okay. So let's say, for example, a photon in vacuum, right? A photon in vacuum is like a photon in vacuum has only 2 degrees of motion, the longitudinal one and the transversal one. But any type of solution for the Maxwell's equation will give you a four-component vector. So you have effectively, from a mathematical standpoint, a four-component vector trying to explain the dynamics of an object, which is a photon, that's trying to move in vacuum that only has 2 degrees of motion. Why complexify situation when already things are complex and work with redundant degrees of freedom, the other 2 degrees of freedom being redundant? So what we say is we gauge them out. And you will learn more in your QFT lectures how the gauging them out prescription takes place. There are many ways of gauging them out, and depending on the kind of problem, you decide what kind of prescriptions you use. But anyways, that's an example. So, okay, let me see to one of the questions. Does Lorentz transformation or group work in every coordinate system? Lorentz transformation, it's coordinate independent, right? It can work in any type of coordinate system. And yeah, any coordinate system. Doesn't matter, cylindrical or x mu just denotes a vector in any coordinate system, whatever you define it. It's independent of that. I am so sorry to interrupt. Of course, you shouldn't be. But what exactly is symmetry? Is Lorentz invariance to change the frames in an example of this something? So, if yes, then what is the generalized idea? Is any intuition or analogy possible? Symmetry is just something that, like, possibility of change that could occur to an object, but it doesn't change. Symmetry allows some things to remain the same, allows key things to remain the same. Like the example I gave of x squared here, like this inner product of x mu dot x mu will remain unchanged. That is a symmetry of the system. Now, this needs to remain unchanged. Otherwise, you fall into the trap of the traditional Galilean transformation, and it's completely an unphysical solution. Like, right, Galilean transformation is only it only predicts nature in non-relativistic speeds, where speeds v are much less than c. But we know from Einstein's theory of special relativity that's not the case. When you go near the speed of light, when v of any object is approximately near to the speed of light c, uh, different transformations have to come to play here, so that your reference frames remain like unchanged, right? That's the notion of it. That's how he built it up. And for that to happen, certain transformations should look a certain way so that the reference frames look the same. So that's the symmetry in this kind of argument. And so I'm hoping I was able to answer that question. Okay. Moving on. So there are many, so just some quick examples, physical often of this part, coordinate transformation, gauge transformations. So like you have, let's say in electromagnetism, you have you have the gauge potential, right? Which is a mu, which is contains the scalar field phi, and you have the three vector A, which incorporates the other, like magnetic fields and the electric fields, of course. This encompasses all. So as I mentioned before, some of it are partly non-physical, So the potential here can be gauge fixed or gauge transformed without altering the nature of the dynamics, without altering at any point the inherent physics of it all. Okay, so that's a symmetry that you're unchanging. You're taking away effectively degrees of freedom that show up in the math when you're trying to solve the differential equation for the dynamics of Maxwell's equation. When you're trying to solve it, you're going to get a type of solution. Now, it is up to you to then realize that no, I'm not supposed to get 4 degrees of freedom. I'm only supposed to get two workable degrees of freedom in vacuum. That's how photons are polarized. So you take away two by gauging them out by different prescriptions, which you'll see in the future. So that is a symmetry, which which is the kind of transformation that at the end of the day does not alter the dynamics of our photon. The photon does not care of what parameters you've lost here. So as long as the parameters that you've lost are unphysical, that they cannot be realized in physics, in physical theories, for example. The other one, I'm sure all of you are well familiar with. If you've taken quantum mechanics, it's the unphysical phase change in QM wave function, right? So when you're trying to find out the inner product of, let's say, psi, it's what? Like dx psi dagger psi, right? Or let's say psi star psi, right? If psi were to be transformed as e to the power I, like some alpha psi, which this incorporates the phase change, psi star would also evolve as e to the power minus I alpha psi. What would happen is when you take the inner product again, let's say this is psi prime star. So psi prime and psi prime. When you take the inner product, you have dx times e to the power I alpha times e to the power minus I alpha psi star psi. These two cancel. These two cancel, and what you're left with is just psi star psi, which is exactly the same as psi psi. As you can see, the uh the inner product of these wave functions, they remain invariant, right? They remain invariant. So this is a common example that all of you guys see. I'm sure, even if you haven't, like this is enough to understand in quantum mechanics. That's it. So there are also proximate symmetries that could show up, ignoring parts of the physics so that we can simplify like future assumptions. For example, one could easily ignore the differences in the masses of the U quarks and the D quarks, right? And ignoring the masses doesn't really change much of the differences of U and D, the masses of U and D quarks are pretty minuscule and they don't change much of the dynamics. And they make the scattering calculations pretty easy. You can cancel them, like the masses M1 and M2 of U. If M1 is the mass of U and M2 is the mass of D, you can cancel them, and it gives you a nice uh, little expression when you're doing the scattering calculations. So those kinds of symmetries you can also exploit. Also, ignoring the effects of electric charge to get the SU2 isospin symmetry of hadronic physics, and all of these things I know might come as like, what is he saying? But they'll come to fruition much later, and I'm not writing them, even though I have that on my personal notes because they're going to be better fleshed out in the future. So yes. So symmetries also, as I mentioned before, and you guys know this from classical mechanics for sure. You guys have taken classical mechanics that symmetries also take part and lead to conservation laws. I'm thankful for that because before Amy Noether, who made this analogy of uh, attributing symmetries and getting conserved Noether's currents for the variational principle to really hold place. Before Noether, we really took for granted energy conservation, you know? Energy conservation, it's just some like mental ansatz that we all as physicists took for granted. We're assuming that yes, this should take place, but we find later on that mathematically a lot of these conservations, like angular momentum conservation, energy conservation, all these things come from different types of transformations that can be privy to your dynamics or your action. Okay, so that's a very important facet, and Emmy Noether is a very highly underrated physicist slash mathematician, in my opinion, to come up with this brilliant notion. Anywho, Moving forward, let's go to Lorentz transformation, which is very important for quantum field theory. So quantum field theory, if you didn't know, is trying to bridge quantum mechanics and special relativity, right? And to do so, you must abide by, of course, the symmetries and the requirements of quantum mechanics, but also the requirements that are gained and um, heavily important to special relativity, which is Lorentz transformation, right? So Lorentz transformation, very loosely defined, it's some four transformation because uh, if you are unaware with special relativity, like we are dealing with four vectors now, not three vectors, because in relativistic theories, time coordinate also it doesn't transform as trivially as in Galilean transformation. So all four components of your vectors of your four-dimensional spacetime are privy to transformations. Okay, so that's why I'll say just keep saying four vectors. So Lorentz transformation, i.e., x mu prime transforms as there's this object lambda mu nu x nu, which would basically keep your inner product uh, x mu dot x mu equals to x prime mu dot x prime mu. Okay, this is very important. So this transformation, there should be something here, and we'll discover what exactly the properties of this matrix here. And this lambda mu nu, this transformation includes effectively boosts, both boosts and rotation. So rotation, uh, the symmetry of rotation, like is effectively you're preserving or conserving angular momentum here. In the case of rotation, it's angular momentum, and there a lot of algebras which I don't unfortunately have the time to go through, but you can see the generators of the Lorentz group giving rise to rotations from those elements of the matrix. Okay, so as I mentioned before, Lorentz transformation plus translation gives rise to the Poincare symmetry. However, for the time being, I will just stick to finishing up Lorentz transformation. Okay, so for Lorentz transformation, we have, let's say, x mu, which contains the x zeroth component and then the ith component. Mu runs from 0, 1, 2, 3, and I, these are the Greek symbol mu, and I runs from 1, comma 2, comma 3. So whenever we have uh, Roman symbols, they're gonna you're gonna omit the zero because zero is always the time part. Okay, this is always the time part, and we're using the metric of plus minus 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 because yeah, that's the metric we're gonna use. Plus minus minus, which is of course different from when you're doing general relativity, but field theorists prefer plus minus minus, mostly minus, which is oftentimes mostly minus signature. Boost is a kind of hit for one specific, it can only happen for one specific kind of coordinate. It can only happen for, let's say, the x coordinate, y coordinate, z coordinate, whereas a translation is an incorporation of all a change in all three of the components. Okay. Anywho, uh, so yes, this is the mostly minus signature. I'm not a fan of this personally, but this is a field theory course. We should abide by this. Okay, so as I mentioned before, the Lorentz transformation must be such so that it leaves x squared, which is defined as g mu nu dx mu dx nu, uh, like invariant, as in x prime squared, which is equals to g mu nu dx prime mu dx prime nu should be equals to x squared, which is g mu nu dx mu dx nu. Now, if you do not remember g mu nu, if I'm to write it in this manner, of the mostly minus signature is 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. This is the mostly minus signature. And so, yeah, that's the metric tensor g mu nu. Okay? And so, or if you're going to write it differently, G00, which is the zeroth component of the metric G mu nu, is of course 1. And Gij is basically equals to minus delta Ij, which is the Kronecker delta, which effectively means that delta Ij, for those of you who are unaware, is 0 if I is not equals to J and 1 if I is equals to J. So basically, all off-diagonal terms, only off-diagonal terms exist for this particular Minkowski metric, G mu nu. All other off-diagonal terms go to 0. Okay. So if you assume that indeed, sorry, this is not x prime. I'm terribly sorry. This is supposed to be ds prime square. Okay. So assuming linearity of Lorentz transformations, which effectively means ds prime square is equals to ds square, then it naturally imbues the fact that your metric tensor needs to change in this following manner: G rho sigma, lambda sigma mu, lambda rho nu, which is equals to G mu nu. This is how your metric tensor must change in order for this to hold true. And in very simple matrix language, this effectively is just lambda transposed G lambda, which is equals to G, where G is the shorthand of like G mu nu, and of course, lambda is just like lambda mu nu. Okay, and the matrix that satisfies the above requirements such that ds prime square is equals to ds square is a particular type of group called the orthogonal group, or orthogonal group called O1, 3. Okay, this 1 is the time and this 3 is the space. We would have called it O4 had it been Euclidean space, which means all the signatures of the diagonal terms are the same, but time is treated differently because of the kind of transformation, a very specific type of transformation that needs to take place, so that the frames are invariant. The dynamics of the frames look the same. So they're called O3, 1. Now, from O3, 1, there is a very specific uh, there's a very specific group that can come out from O1, 3, which is SO1, 3. Now, for SO1, 3 to hold true, we must have the following conditions to take place, which is the fact that the determinant of lambda must be equals to 1, and the 0, 0 component of lambda, which is effectively the time component, right? 0, 0 component must be greater than or equals to 1. Okay. Now, as this specificity imbued on O1, 3 gives us SO1, 3, as in SO1, 3 is a subgroup of O1, comma 3. Now, what is a subgroup? Very, very fast. Give you a definition of what is a subgroup. Subgroup is, subgroup H is defined for a group G where H belongs to G, as in if you have a big set here G, there exists a smaller set H. Now it could, okay, there exists a set that is inside G, which we call H, is naturally defined as a set of elements belonging to G, which is also a group. So, in very simple language, H belongs to the bigger group G, and H itself is also a group. So it means the group G is defined for a specific operation, right? For a specific operation, and it's closed under that specific operation. It has the identity element and the inverses at place. So H must contain that specific identity element of G. Otherwise, of course, it cannot be a group in and of itself. A subgroup has to very importantly be a group at the end of the day. And all the elements of H, little h, all the little h's of H, the big H, must have their unique inverses also in the subgroup H for it to be a group. Very important other facet. So, yeah. Now, a trivial subgroup would be that this H belongs to G. You can trivially have it be encompass the whole set G. Now, that's a trivial subgroup. The subgroup that is more fun to play with is the subgroup where H is smaller than G. And a very important point is for any subgroup H, there exists the following equivalence relation. Where G is equivalent to G, GI is equivalent to GI prime, where, yeah, if you have the GI prime is equals to GI of some H, okay? For H that belongs to the subgroup capital H. So, yeah, this is what is known as an equivalence relationship, yeah? And this is how you denote an equivalence relationship, where how the GI prime is related to the GIs. So each equivalence class GI, this is how we denote it as the equivalence class, defines a left coset. What is known as a left coset? And has H many elements. That's the dimension of the group H, however many elements it has. Of course, E also belongs in H, like the identity element. So for right cosets, not left cosets, right cosets, we have the complete opposite of this equivalence class, as in GI is equals to HGI prime. Okay? Instead, thus forming what is known as the coset space. Okay? So the coset space is defined as the following. This is the kind of nomenclature that is always used when defining coset space. G set cut H, basically G equivalence is equals to some G multiplied by H, where G belongs to the big group G, and H is of course here. It's denoting. You might say, why are you multiplying an element of a group to a group? It just big this just denotes that any element of the big group H basically that can be possible. Okay, so okay, where G is equivalent to G prime, if of course G prime is equals to GH for all H in capital H. Okay, so this is a very important thing to know moving forward. Just the definition will suffice. And the dimension of this coset space is, I give without proof, is G by G set cut H, like the dimensions of GH, G set cut H, which is effectively just the dimensions of G divided by the dimensions of H. Of course, when you're trying to define dimensions, dimensions are going to give you just natural, real numbers, right? That's the definition of dimensions of sorts. So the dimensions you're going to get is like however many elements you have in your big G divided by the however many elements you have in your subgroup H. There's a subgroup of your big G. Okay, moving forward. Uh, moving forward. So I spoke about the structure of the Lorentz group a little bit, and that the Lorentz group is effectively like the SO3, 1, which is the Lorentz group. SO3, 1 is known as a connected subgroup of O3, 1. Okay. Now, before we move forward, I'll try to give some more examples of very useful uh, group theories that are gonna come to play, basically. Very importantly are the notions of matrix groups, right? Matrix groups are very important before we move on. So we have matrix groups. One group we've already spoken about, it's the orthogonal group, which is the O3. This is what is known as the orthogonal group, or ON. It groups, or ON, i.e. orthogonal group of n dimensions, like it's an n-dimensional one. It's basically a set of, or the ON group, this is the name, is some specific, no, it's just not, it's not some specific operation, it's just whatever subgroup you have, you know? It's like it's whatever subgroup you have, knowing that like your equivalence holds true. Okay. So ON is an orthogonal group of n-dimensional n-dimensional n by n m n by n matrices, which we denote as M, such that M transpose M is equals to 1. If you're unfamiliar with what transpose means, like effectively all the rows become columns, columns become rows. That's the kind of transformation that occurs when you do a transpose of a matrix. Okay, so n by n matrices. No, actually, this is wrong. It's not n-dimensional. It's a wrong statement. Okay, and these sets of matrices are closed under multiplication, since of course, like you have this following property of when you do transposes of matrices, is it M1, M2? Whole transpose is M2 transpose M1 transposed. And of course, as I mentioned before, for general special orthogonal groups, SO means special orthogonal groups. For SON, we must have the determinant of M should be equals to 1. And of course, the general invariant quadratic, if you're also unfamiliar with what it means by n by n, it means like you have n many rows and n many columns, right? So it's n and n. It has to be an even dimensional square matrix, because if it's not a square matrix, can somebody explain what could be a problem? If why do they have to be the same dimensions, the rows and columns? Couldn't we work with in all kind of matrix groups? You will find that all the matrices, a bare requirement is that the number of rows and number of columns are important, are have to be the same. Transpose multiplication won't make sense. Uh, you're right in the context of orthogonal groups, but there are other matrix groups which do not have the requirement that M transpose M is equals to 1. You know, I can give you a very generic matrix group that does not have this requirement, but still require the product of the matrices to be of the same dimensions for rows and columns. It cuts between the definition of group theory. Inverse. If you have n by n, like otherwise an inverse does not exist, right? It's as simple as that. So it's a privilege to have a mathematical object for which inverses really exist, you know? And for matrices, if the dimensions are not the same of the row and column, you will not have an appropriate inverse, right? Inverting it is not possible. What does what does the inverse mean? Let's say you have matrix M. M times M inverse should give you the identity matrix, right? The identity matrix is 1, 1, 1, 1, blah blah blah, dot dot dot, however many, and then zeros here, zeros here, right? That's effectively what it's trying to say. Now, in the orthogonal group, what happens is the inverse of the matrix is just the transpose of the matrix, right? That's the orthogonal group. That is the key beauty of the orthogonal group, or the key property of the orthogonal groups, to say so more precisely. So, but yeah, they have to be of the same dimensions, regardless of whatever kind of matrix group you're dealing with. One thing has to stay the same. For it to be a group, the inverse must exist, and not for if you change the properties of specific matrices, you might not see that the inverses could exist, right? Okay. Any kind of high energy physics calculations, that's something that mathematicians don't like, is the assumption that the inverses do exist. But, we get our results however we can.
It's
Okay.
very tedious to compute inverses.
It's highly tedious to compute inverses. But if the inverses don't exist, there's nothing to compute.
Right.
If the inverses themselves don't exist, there's nothing to compute. You have hardcore mathematics that is completely stopping you from doing any kind of thing that is physically relevant. You cannot exploit symmetry at all if your inverses don't exist. But there are a lot of work being done, because these are examples of a very specific group theory, and all of these things are examples of a very specific type of symmetry called one-form symmetries. But it's the highly non-trivial and crazy notion is that higher form symmetries of higher and higher. I won't go into the details of what higher form symmetries are. Just take for granted that what I'm speaking of, what we're going to learn for the time being, they're known as one form symmetries. So in any kind of higher form symmetries, what you find is the symmetries are non-invertible. So for those, still a lot of work is being done uh, in higher form symmetries and non-invertible symmetries, and what they hold true for dynamical systems of all sorts, not just in high energy physics, of all sorts. Symmetries can be exploited in many aspects of like economics, biology, many aspects. Anything that is dynamical can be privy to symmetry arguments. Huh? So thankfully, we don't have to deal with non-invertible symmetries. We have beautiful invertible symmetries here at our disposal. Okay, moving on.
Yes.
So the general invariant quadratic form is just when you take the norm, the inner product, and the norm is just x transposed with x, right? It preserves this inner product, where of course x is an element of n-dimensional real number, right? And I mean, if it's not an n-dimensional real number, yeah, you're not gonna get a positive semi-def like positive definite form for the inner product. Inner product must give you a positive definite form. If it's not Rn, if it's complex or imaginary, you're not gonna get the requirement of the norm being positive definite. You're destroying that, right? And that is unphysical. So yeah. Moving on. This is the orthogonal group. Moving on, we have the unitary group. Unitary group, denoted by capital U of n, which are complex n by n, again, n by n matrix, of course, such that M, again, M is the matrix that belongs to the group UN, right? M, not, this is not a T. For those of you who know, this is called a dagger, right?
Yes.
This is called a dagger. So M dagger M is equals to 1. So what is this dagger operation? It's effectively, in matrix terminology, is just the complex conjugation of M and then transposed. Okay? This is T transposed, which is equals to M dagger. Okay? Now, there are fascinating cases where M dagger is equals to M. As in, when you transform the matrix, you do a complex conjugation, and then you do a transpose of it, you get the same matrix back. Does anybody know what these types of matrices are called?
Diagonal matrices?
Hermitian matrices.
Harmony.
Exactly. Hermitian matrices. So Hermitian matrices, yes, and they will come to importance when we're going to talk about like they incorporate spin Hermitian these type of matrices, and when we talk about the very specific SL2C group, was when we're gonna come to terms with the Hermitian matrices. Okay, for the time being, unitary groups require this. Okay. And of course, uh, under it's the operation is closed under multiplication. M1, M2 dagger is just equals to M2 dagger, M1 dagger. This is a very, if you know already that this is a property of matrices, this is a very easy thing to prove, right? Complex conjugation doesn't really change anything of the order of multiplication when you break the brackets. Then for the unitary group, we have another subgroup, right? We have another subgroup which is of the likes of the SO 3,1, a connected subgroup which is called the SUN group, which requires the determinant of M to be equals to 1. And of course, again, the invariant quadratic form is, you take the norm, X dagger X instead of X like M transposed M, or like, yeah. So sorry, X transposed X. And here X is not a real number. They're of course complex valued, because of course unitary group are complex n by n matrices, right? So if it's a 2 by 2 matrix, it's like A plus BI, C plus DI, E plus FI, H plus GI, say, for example, right? These are complex values. And a very fascinating property of specifically SO2. Does can anybody tell me what SO2 stands for? Like, what kind of a transformation is SO2, for those of you who might know?
Electroweak theory transformation.
So that's SU2.
SU2.
SO2 is special orthogonal.
Right.
So SO2, yes, Adil, perfect. It's a two-dimensional rotation. It's a special
Rotations.
orthogonal group. It's a group responsible for the transformation that leaves 2D coordinate systems rotationally invariant. Okay? One amazing aspect of the SO2 group is that it is isomorphic. I'll get back to this big word, isomorphic, to this group U1, as in where if UN denotes n by n matrix, U2 is a 2 by 2 matrix, U1 is a 1 by 1 matrix, which is just a real number, which is just a complex number, you know? It's not a matrix. 1 by 1 matrix is just a number. So uh, this, they're called isomorphic to each other. Now let me uh, before I try to show you how, let me just define very quick what isomorphism means. Okay, so isomorphism is a structure preserving map between two different groups. Groups, of course, they need to have an inverse that have an inverse. Not that the matrix, the elements inside the matrix has an inverse, but the map has to have an inverse. If you're mapping from one group to another, you have to figure it out to go back to the group that you mapped from. That inverse has to exist, not the inverse of the element of the group. Okay, I'll flesh it out better. Different groups that have and that has an inverse. Sorry, have. Okay, so we have G and H. They're groups. They're two distinct groups. They're two different groups. Then there must exist a map. Then let's say a map exists, right? This map takes phi from G to H. Effectively, you have this set G, which is not the same as H. I'm using H here. H does not, again, to reiterate, H is a completely different group with different group properties, different group elements. It could be different. There could be like mom here, and there could be 49 here. Completely different elements with different operations could be completely different. Okay. So this map takes elements from or sets from G to H. This is this map, phi. Okay. So given this mapping phi is known as a group homomorphism. Sorry, this mapping phi is an isomorphism if and only if there are two lemmas that need to be validated for it to be an isomorphism. If for one, there exists a homeomorphism, a homeomorphism. What does that mean? It means, let's say you have phi of G1, G1 dot G2. It's can be written as phi of G1 dot phi of G2. So let's say you have G1 here and then G2 here. Okay. So G1, these are elements of the big group G. So uh, what is the left-hand side saying? It's when you multiply G1 dot G2, and let's say, for example, multiplying G1 and G2 gives you this element G3. So this, when mapped using this phi, this mapper phi, is mapped to, like, if phi of G1 mapped here, phi of G2 mapped here, and when both of these phi of G1, phi of G2, when you multiply both of these inside here H, they give the same point here. Okay? So that is what it means to be homeomorphic. And that happens when your mapping is a complete homeomorphism of sorts. So homeomorphism must exist, and very importantly, bijectivity. As in, phi is injective. Can you explain the relation between invariant quadratic forms and their groups? Invariant quadratic forms are like these specific, like, uh, okay, in quantum mechanics, right? When you do that type of norm, what are you leaving invariant? Can you tell me? Or anybody who has the answer. When you do uh, the norm of psi and psi, what is being left invariant? Probability, right? The probability that the particle or that wave function exists, right? So that you're assigning to that the brilliant physicists in the time when quantum mechanics was built up. They built up this type of wave function, and they understood that the quadratic form of these wave functions, especially when you do, of course, the psi dagger and then psi, you will find that probability is something that is unchanged. And no transformation of the particle should change the probability distribution of finding that particle, right? At the end of the day, you're in quantum mechanics, particle number is conserved, right? You're not going to destroy the particle by doing anything to the particle, or you're not going to like destroy completely the wave function. You might collapse the wave function in trying to observe it, but you're not going to destroy the wave function completely in its kind of interpretive probabilistic nature. So what they realized is that quadratic form of these wave functions, size, basically leave the probability invariant. In this case, when in terms of Lorentz transformation, it's the ds squares that you're leaving invariant. Something has to be left invariant, and it depends on the kind of theory that you're working with, that where you incorporate your invariance to. Okay, I hope I was able to answer that question. And in relations to the groups have elements that leave those specific quadratic forms invariant, right? The phase change in quantum mechanics. Phase changes are elements of the group U1. So what does that tell you? U1 when acting on psi, U1 when acting on psi just gives you psi, right? It doesn't give you psi, it gives you some psi prime, but it leaves your psi invariant. As in, it's the same as psi prime and psi prime. So this incorporation of U1, when you're just doing like, what is happening here? Psi, and then you're doing some, it's transforming as you're applying some U1 operation to psi, and another U1 operation to psi here on the pet and on the bra. what you find is that this U1, it leaves this quadratic form unchanged. I hope I was able to answer that question. U1 is basically just your phase change, right? E to the power some I alpha is your phase change, as we saw with uh, explicit calculation just stays the same. Anywho, getting back to isomorphism, the second axiom that has to hold abjectly true is bijectivity. Phi is injective. This mapping has to be injective, as in it has to be 1 to 1. Each element has to map 1 to 1. Okay. And surjective, which means onto. Okay. So an inverse map completely of H gives you G. As for phi, G gave you H. Now, if these two hold true, you have yourselves an isomorphism. Now, getting back to the thing I was talking about, that SO2 is isomorphic. This is what we call isomorphic. Okay, so of course, if these hold true, G is isomorphic to H. This is the symbol of isomorphism. Okay, so what I was saying before is that SO2 is isomorphic to U1. How so? SO2 is what? Let's write the matrix for SO2, like a general SO2 matrix. It can be written like this: cosine theta minus sine theta, sine theta, cosine theta. As we can see, the determinant of this matrix is equals to 1. So it is indeed a special part of the orthogonal group. Like it's the subgroup of the orthogonal group, since it's specified here, the determinant is 1. Because what do you have? Like det, let's say this is m. Det of m is cosine theta squared, cosine squared theta plus sine squared theta, which is just 1 using the trigonometric identities. Anywho, and of course, these thetas are defined, right? They're defined, let's say, from 0 to 2 pi. Here, very important. If you include 0, you must disinclude 2 pi. If you don't include 0, then you must include 2 pi. Okay? For the time being, I include only 0, and I leave 2 pi alone. What this claim is that this SO2 has a 1 to 1 correspondence with the general element of U1, which you can make it look like e to the power I theta, okay? Where theta is again defined as 0 theta to 2 pi. If it's not defined like this, bijectivity will be lost, right? If bijectivity is lost, you don't have an isomorphism anymore. Okay, so as you can see, right, this exponentiation itself is your map, right? E to the power theta is exponentiation is your map. And the beautiful part of the exponential function is the fact that uh, this holds very easily and trivially true. This holds very easily and trivially true. So you do have a homeomorphism, and because of the way you defined your thetas, you also have bijectivity. So they are so you've proved both of these cases to be true for the mapping of using an exponential function, right? You're taking e to theta to get an element of u1, okay? Anyway, so what I'm saying, and it's just so that topologically, as in geometrically, like equivalency, basically, geometry equivalency, U1 is equivalent to S1, which is the circle. S1 means circle, if you're unaware. So that there are more detailed calculations. Take it with a grain of salt for the time being, because I'm going to show you also an isomorphism between SL2C and SO1, 3, right? That's very important as well. So there's this done. Now I'm going to go into the notion of compact and non-compact. Okay. Compactness, very easily, I just want to say, like, it's that, like, groups like SON, SUN, and, like, let's say UN, right? They are compact. What do I mean by that? Is that very simply put, very trivially put, it's that the natural parameters, they vary over a finite range, right? Like, you see, for example, here, theta is only varying over a finite range, 0 to 2 pi. There are no infinites here. Everything is finite. This rotation is finite, giving you a finite, like, circle kind of rotation, right? So a compact group are parameters that incur finite inputs. So on the counterpart, there are also non-compact groups. Can somebody tell me if the Minkowski, right, which is part of the SO1, 3 group, given that it's a Minkowski, and remember, Minkowski is supposed to define our entire universe, the vacuum and everything, our entire cosmology of our universe. Is SO1, 3, just from knowing that, is SO1, 3 compact or non-compact?
It's non-compact. The coordinates could be infinite, right?
Perfect. It's non-compact. The coordinates are indeed infinite. They can range from, effectively, depending on what coordinates you choose. If it's, let's say, for example, you choose the spherical polar coordinates, it can go from R can vary from 0 to infinity, and where the difference in parameters is still infinity. If you're using Cartesian coordinates, which is X, Y, and Z, it'll vary from minus infinity to infinity, where the difference is, again, infinity, right? Infinity minus anything, you'll still get infinity. Okay. So yeah, SL1, 3, these are non-compact groups. Okay. And another important group, which is the SL and R, or SL and C, we will come back to defining the what is known as the special linear group. Special linear group. This is a subgroup of what is known as the general linear group, GL, NR, or of course SL. It could be C, GL, and C. What these mean is, like, these are n by n matrices, with complex entries. And here again, n by n matrices with real entries. That's the difference. Okay. So as I was saying, yes,
Special linear.
yes, they're called special linear. I haven't defined yet what makes them, why this specific group is, like, yes, it's called special linear, but why is this, what is the defining motive of this group? Like, before, you had orthogonal group, which is defined by the fact that M transpose M is supposed to give you the identity. Our unitary group, which is the M dagger, M is gonna give you unitary. I still haven't defined what makes special linear groups so different from the other matrix groups.
Right, right.
Yeah. So SLNR is unboldened by this notion of compactness, right? It's untethered. And so SLNR or SLNC are non-compact. There's also another group, which is the group called the symplectic group, like, let's say, SP2R, I'm not going to go into complete details for the symplectic group, but symplectic groups are defined as like matrices which are part of the global linear group 2, R, where M transpose the symplectic part and omega M gives you omega. Again, I'm not going to go into details. For example, the matrix form representation of this group, an element M, effectively looks like this: cos hyperbolic theta, sine hyperbolic theta, sine hyperbolic theta, and cos hyperbolic theta. And we know these hyperbolic functions can take inputs that range from minus infinity to infinity. And yeah, they're the range of parameters that you deal with when you're dealing with like the real symplectic group. This is the real symplectic group. There's also complex symplectic group. Okay. To keen viewers who have done the special theory of relativity, you remember complex in Lorentz transformation, you can also uh, write the matrix in terms of hyperbolic functions. You've seen this, I'm sure, or some of you have seen this. Yeah. So it's exactly because of that. You cannot express uh, exactly rapidity as well is incorporated to those matrices. You cannot have Lorentz transformation to be have parameters that are compact in nature. No, 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 no. That cannot be true. Uh, like you have to incorporate non-compactness to SO1, 3 because you have to, at the end of the day, describe the universe at hand. So yeah. Anywho, that's the notion of compact and non-compactness. Now I want to show you uh, the nitty-gritties of the SL2C group. Okay, so there exists a very important isomorphism, which is that SL2C mod Z2. Yeah? So this means, again, as I defined before, the right coset, right? It's this. Uh, wait, yeah, it's this. It's the coset space. Effectively, SL2C, which is the special linear group, right? The special linear group has incorporated inside it Pauli matrices. I'm going to go in detail down below, but let me set some things up here. They have very important notions as well, and they are Hermitian, of course. So, anywho, uh, SL2C mod Z2, where Z2 is basically -1 and 1. Okay, they're two-dimensional identity matrices, but here you have -1 and here you have 1, and you're modding these two with SL2C. Okay, and if and only if when you do this, do you get an isomorphism with SO1, 3. Okay, and I'll flesh it out how they are isomorphic to each other. I'll show you now here. So SL2C, they are n by n matrices that are built up of Pauli matrices, right? If you remember Pauli matrices, they are these three beautiful matrices: 0, 1, 1, 0, which is sigma 1. I'm using this specific notation. I forget if this is the direct notation or not, but I just took it from my memory. I forget the name. And then sigma 2, 0, 0 minus I, 0. You have sigma 3, which is 1, 0, 0, minus 1. Okay. Very important is that when you have the matrix X, which belongs to SL2C, which is built up of these Pauli matrices, okay? And very importantly, you have X, which is built up of this component X0 multiplied with the identity matrix plus sigma 1 x1. Again, remember, this is capital X. Whenever I have these top bars, I'm denoting a capital X, and this denotes like the coordinate. X0 denoting, of course, time. Sigma 1 x1 plus sigma 2 x2 plus sigma 3 x3. Okay? And this matrix X then looks like, if you actually add all of these things up, what is it like? The identity one is just like you get here x0, 0, 0, x0 plus x1 times sigma 1 is like 0, x1, x1, 0 plus this part is now 0 minus x2 minus I x2 I x2 0 plus x3 0 0 minus x3. And if you add all of these up, you get x0 plus x3, x1 minus I x2. You have x1 plus I x2, and you have x0 minus x3. Why do we do this like this? What is the importance? Very succinctly, the fact that the adjoint of x is just x, as in you're now, with the aid of Pauli matrices, you are building from these Pauli matrices uh, Hermitian matrices. SL2C requires it's matrix elements, not matrix elements. The SL2C is a group, and its element is, of course, a matrix. These matrices must be Hermitian. That's its basic property. That's what differentiates it with the other types of groups. Okay, so Pauli matrices, of course, here we're not using just the three-dimensional counterpart to Pauli matrices. We're using four-dimensional counterpart to Pauli matrices. As in, you have to define separately. Let's say sigma mu. These are not complex elements. The complex elements is baked into the Pauli matrices in and of itself. As in, these off-diagonal terms need to be. You see, just because like okay, no, that's not what you asked. But like a real number is also a subset of a complex number. So just because like an element is said to be defined as a complex number, need not have the imaginary part baked into it. It can just be a real number, in that the imaginary part is just zero, right? So yeah, for it to be Hermitian, it has to have this structure where where the imaginary part is non-zero only in the diagonal with the following form and only attached to x2s. And that too, here you have to have a minus sign, here it has to be a plus sign, and x0 must add to x3, and here x0 must subtract to x3. Okay? And x0, x1, x2, x3, these are just real numbers. Okay? Like x0 is the time component, x1 is the, let's say if you're doing Cartesian coordinate system, x0 is the time, x1 is x, x2 is y, x3 is z. Okay? But where the complex term comes from is that the final matrix that makes up SL2C has to have complex entries. You know, they have to have complex entries. Okay, in some form or another. It's defined to have complex entries. Okay, so we have to have a four-dimensional counterpart to the very to the Pauli matrices, in that we have this specific combination. Why this specific combination is gonna it holds true once you do like brute force calculations and find out why this specific calculation, why this specific form. You define sigma mu as the identity, and then sigma I, okay, and then which is, of course, since they're Hermitian, which is equals to sigma dagger, and then you have sigma bar mu, which is defined as the identity, and then minus sigma I. Okay, and I, of course, runs from, which is of course, yeah, here sigma. But I got I, of course, runs from, well, 1, comma 2, comma 3, because we have what, three distinct type of Pauli matrices that are possible. Okay. Moving forward, we have a couple of definitions. So these both sigma and sigma bar sigma mu form a complete set of 2 by 2 matrices for which you will find that sigma nu bar plus sigma mu bar is equals to 2 g mu nu multiplied by the identity matrix, because g mu nu is like it's a matrix element, not the metric itself, not these are all matrix elements when you give the nus and the mus and blah blah. Anywho, and then also you have sigma mu bar, sigma nu plus sigma bar nu, sigma mu is equals to 2 g mu nu multiplied by the identity matrix. Also, an important facet of SL2C is that the trace of sigma mu, this is pretty trivial. It just requires brute force calculation. Just do it for mu and nu is equals to like the form of the sigma matrices, and you'll find you're bound to find this relation to hold true. Okay, and also moving forward, you have the trace of sigma mu, sigma nu bar. Again, remember the bars are defined as just the a negative sign multiplied to the three sigma matrices. That's what the bar denotes. It's the bar doesn't mean complex conjugation here, right? The bar just denotes that there's a minus sign multiplied to it. Okay. So the trace of sigma mu and sigma nu bar gives you 2 g mu nu. And yeah. So therefore, if you manipulate this properly, for a 2 by 2 matrix A that belongs to SL2C can be written as A equals to 1/2 trace of sigma bar mu A and sigma mu. Okay? Just comes from manipulating this. Okay, moving forward, let's now break down how really is SL2C isomorphic to SO1, 3. SO1, 3 is supposed to preserve the invariant length, right? The length squared, which is ds squared, right? That's the length. ds is length, and the length squared, which is what is being what is made invariant. So
Invariant.
yes, the isomorphism we can define first by noting the following correspondence, okay, between uh between the 2 by 2 matrices. So there's a correspondence built between 4 vectors x mu and Hermitian matrices capital X, where we're trying to figure out where there has to exist a map, right? Where it takes our 4 vector x mu. This 4 vector, of course, belongs to SO1, 3, to go from the 4 vector x mu to a Hermitian 2 by 2 matrix, which belongs to SL2C. Okay, 2 very distinct groups, and X is defined by sigma mu, and this sigma mu Pauli matrix multiplied by four vector x mu. Okay, you can have that where x mu is just equals to the trace of sigma bar mu capital X matrix. Okay, so doing that, if I am to if you recall where we did this calculation and we found that the general matrix of SL2C takes this form, and if you try to find the determinant of this matrix, the determinant of this matrix is just what? X0 plus X3 times X0 minus X3 minus X1 plus I X2 multiplied by X1 minus I X2. You do this pretty easily, you will find the solution to come like this: X0 square minus X1 square minus minus X2 square minus X3 square. Does this look familiar?
Length square.
Exactly. It's the invariant square form that you get from SO3, 1, which you're getting from SL2C. If you have these Pauli matrices, multiply with four vectors x mu in this form. So the determinant of X we find gives us as our invariant square form back, which is x square ds, which is that x square is equals to g mu nu x mu x nu, which is what we want, right? In similar fashion, you will also like further defining the fact that like there exists an X matrix X bar, which can be built up with sigma bar mu. And remember, sigma bar mu is just the identity element and the minus sigma I kicked in together. And of course, there's an X mu. You utilize these two definitions. You utilize these two definitions. You do some pretty basic algebra. You will find that X multiplied by X bar, again, this is the matrix X, is just equals to X squared of 1. And in same fashion, X bar multiplied by X gives you the same X squared. So we see that the invariant square form of SL2C just gives you the invariant square form of SO1, 3. So there exists acute kind of isomorphism. Of course, there are more comments, and for any A that belongs to SL2C, we may use it then to define a similar linear transformation as we had to Lorentz transformation that gets us from X mu to X prime mu without again leaving the square form unchanged. It leaves the square form unchanged, as in the linearity is conserved. And so because we've shown that it is indeed conserved, this must be a real Lorentz transformation. It's a type. It's this isomorphism gives us the feeling that, okay, SL2C is also preserves the kind of structure that SO1, 3 preserves. What does that, how is that useful? Why am I babbling on about SL2C? SL2C? It's that spinors, which are not scalars, they're not vectors, they're not tensors, they're their own specific type of object that are determined by SL2C algebra. Spinors are the fundamental objects. Let me write it down. Spinors are the fundamental objects that define transformations that leave fermions unchanged. Right? Our world is not just bosons. For us as humans to exist, we must be made up of fermions. We're built up of fermions at the end of the day. Yeah. So any fermionic transformations, like they only transform because they come in doublet pairs, not in trivial fashion like bosons or like tensors. Okay, tensors are not trivial. No, none of these are trivial, but those kinds of understandable fashions. You need the algebra of SL2C. And given the fact that SL2C is isomorphic to SL1, 3, you find that spinors are not only are they acute at explaining fermions, mathematically explaining fermions, but they're also Lorentz invariant. Of course, these theories, all of them have to be Lorentz invariant. SL2C preserves Lorentz invariance, as we've seen. SL2C mod Z2, of course. SL2C mod Z2, they preserve Lorentz invariance. So building up spinorial algebra with SL2C in mind, you can incorporate relativistic fermions to your relativistic Coulomb field theory, which tries to explain your scalar bosons, your fermions, your vector bosons, and unfortunately fails to explain tensor types. So yeah, that is kind of all I wanted to explain today. So yeah, any questions, any comments, anything in particular you would like to tell me?
Are you
That's all for
going to give
today.
us lecture notes? Sorry.
I will upload this lecture notes if that's okay.
Okay. Okay.
Uh,
All
I,
right.
I will
Thanks.
upload I will upload because the personal one that I took is a little it's scraggly. Uh, I can try and organize my personal notes, which are they're a little disorganized in the way I noted them down, but they just have more words to it.
Hmm.
The note that I took that is displayed to all of you, I'll stop uh, I'll stop recording.